Okay, hey, thanks everyone for coming. Welcome to Event Detection Pipelines with Apache Kafka. I also know that this is the last session of the day, so people are probably ready to go and do something else after this. It's probably been a good day. But the next 30 minutes or so hopefully will be interesting and informative. So I'm going to try to do my best to get through all the content, and then, like everyone else, we'll do some questions at the end. So let's get started. This is sort of my, wait, I gotta figure out the slide thing. Okay, my obligatory about me slide. I'm a senior systems engineer at Cloudera. I focus mostly on data ingest and the financial services vertical. I am a Kafka contributor. Doesn't mean that I'm a full-time developer on the project, but have taken a particular interest and so try to contribute in the community any way I can. I encourage any of you that are so inclined to do the same. Patches are always welcome. We have a pretty active community right now. By way of background, I spent most of my early career doing Oracle-related stuff. So as a database administrator, spent a lot of time with RAC and then moved into development, ETL development, front-end development, back-end development. Most importantly, though, I'm father of Charlie Grant. It's the little guy in the middle, and a saint of a wife who watches all of them while I romp around Europe. So today what we're going to talk about is sort of how we got here a little bit, why Kafka. I'm going to go through a use case pretty detailed. Then we'll talk about some challenges of that use case and then some sort of tips for deploying Kafka in a real production environment. Additionally, I promise I will say each one of these words. So if this seems interesting to you, you should stay in here. If not, maybe it's not the right talk for you. But if I don't mention all of these, I promise I'll buy you a beverage later. So this is sort of how we got here. Almost every Hadoop use case that I know of started off with ETL offloading. Not always, but a lot of the times it starts off with some kind of ETL offloading from some type of RDBMS, and then maybe we take the results of that and put it back into an RDBMS. And we realize, of course, that Hadoop can integrate with many other applications, so we start pulling in data from file transfers. Maybe over here on the right side, we start building applications that actually use Hadoop directly. Somewhere along the way, we determine that we can do direct reporting off of it as well. But basically, we kind of start down this batch route and start building applications on top of it. But in reality, our applications end up looking a little bit more like this, right? As we start building out these applications, we realize that it's a little bit simplified, right? In reality, all these apps have interdependencies, particularly as organizations move towards services and microservices, right? Unless we're fairly disciplined, they all have maybe different ways that they talk with one another, and all of them end up being somewhat interrelated. Not to mention the fact that a lot of times it's not just a technological barrier, but in large organizations, which is where I tend to work, this is sometimes sort of political or organizational as well, right? But one thing that's definitely true is we could probably all benefit from using a little bit more of a integrated data exchange format, right? Because when something goes wrong or some change happens in a downstream system, if you have all of your applications that are fairly tightly coupled together, it makes for a little bit of a brittle architecture. And so that's a little bit the impetus for Kafka. If you were in the Koya talk a minute ago, some of this was covered. Just by way of hands, how many people have used Kafka or are thinking about using Kafka just by way of hands? I guess like pretty much all of you. And I'll skip the details of this stuff. I mean, you guys know that it came from LinkedIn, and importantly, at least to me, the important parts of it that are it's high throughput, low latency, and because of the way it's designed, replicated and distributed. And when I have agnostic messaging here, it's a little bit of a weird term, I guess, but my only point here is just that producers don't necessarily or don't care about consumers downstream. Consumers don't care about producers, they just care about the data. And in fact, consumers don't actually have to care about other consumers of the data as well. And it standardizes, it can, if you integrate it in the right way, it standardizes a format and delivery. And so it really gives us a solid foundation on which to build these type of systems that we're going to talk about today. So just by way of architecture, you probably have all seen this picture before. I lifted this from somewhere out there on the internet, I think Joe Stein. Producers produce, just so we're talking about terms, producers produce to brokers. and consumers consume from brokers, and all of this is sort of custom code, right? You're writing something to push into Kafka, you're writing something to pull into Kafka, but my sort of key point about Kafka is it really does try and decouple these data pipelines so you don't have these direct application-to-application dependencies as you're building out these type of systems. So as I mentioned, I mostly work in consumer banking. So today what I'd like to do is talk a little bit about event detection and fraud detection in particular. However, I think that this type of architecture is actually pretty broadly applicable. Like I said, I know the most about it as it relates, swiping credit, debit cards, and fraud transactions in banks. But anytime that you need to build a system that sort of takes data in real time and then ingests it into Hadoop, I think this architecture will be pretty applicable. So when we start talking about event detection and fraud, there's really kind of two different ways to look at it, and the fraud system's actually pretty broad. The first is offline, and another way to look at this is that offline fraud detection is human or operator-driven, and I consider online detection to be some sort of automated fashion, right? So what we're going to do is briefly kind of cover the offline just to show the total architecture of the system, and then we'll get into sort of using Kafka in context as well. But when we're talking about offline fraud detection, we're talking about things like model building, discovery, forensics, case management, pattern analysis, those type of things. So what we want to do is we want to build, let's say, this multi-channel fraud application. And when I say multi-channel, these are just a sampling of some of the boxes here, right? We have online transactions, mobile transactions. These days, most of the time, if you get a check, you can take a picture of it, upload it, and that'll get directly deposited into your bank account. Of course, ATM transactions. I realize that here in Europe, it's a little bit different because there's chips on the credit cards and that kind of thing, and then the point of sale as well. So actually, doing it during the card swipe. So the first step in that layer is that each one of these systems tends to have a little bit different of an initial format, and so we have some kind of integration layer that basically takes the transaction from whatever source format it comes in and converts it into our canonical event processing message format. The next step is our event processing, and again, I've kept this kind of high level for now. We'll get down into the technological components in a moment. But we do our event processing. In this step, we basically take in the transaction, make some kind of decision about it, and then return the result back to the source system. Right? So that's pretty easy, right? But our next step is that we have a sort of a persistence layer, and in this case, we persist into a repository, and this lets us do reporting, forensics, analytics, all those kind of things. And so at this point, forgive me, I've kind of overlaid a technical component in a functional diagram, sorry. But of course, we use Hadoop, right? And so we may have some supplemental information from a mainframe or RDBMS that uses that feeds into some of our use cases, and for processing, there's various tools up there, whether that's Impala, MapReduce, Spark, third party. But really, the output of our system is kind of threefold. Number one is that we update based on patterns. And so basically, it's this offline system. We have our analysts who are searching for patterns, and they're basically pushing rules back into our event processing system. So these are things like, if it's this type of threshold, or if I see this type of transaction during the event flow, I'm just going to check a rule, right? Just a static rule, and we can put that into the event flow. And then the other is that we can use tools like R or SAS or Spark, as we kind of move forward, to actually update our model, build our model, and push those back up into stream, right? So we're kind of using Hadoop for the standard sort of machine learning model building type tasks. And then also we have, basically we've built applications on top of this where we can push specific updates out to case management. As I mentioned before, fraud as a system is actually very, very broad. There's a lot of the work is actually in case management, handling outbound calls. If you may not decline a transaction as it's coming in. A lot of times you'll just flag it, and so you'll need to make sure that you send a notification either via text or email or phone call, so that someone's standing there, their card gets declined or doesn't, but you get a call pretty much right away. So that's sort of the main outputs of that, and then that kind of brings us to our online system. In the online system, we're focused on things like data ingest, enrichment, and I'll talk a little bit about what I mean by enrichment, and obviously the early warning detection areas, and then persistence into Hadoop as well. So enrichment is, there's a box up here that says reference data. So when a transaction actually comes into your, let's say, consumer banking or whatever, you swipe the card, you may not actually have all of the information that you need to make a reasonable decision about whether or not you're going to either decline or flag the transaction. So what we have is our customer reference data and probably some other stuff too, like location-based data. So there's a couple of different use cases. Think about how frustrating it is when you're traveling and you're actually traveling and your card gets declined because you're in some other country or some other location. This happens quite frequently. In fact, happened to me here. I actually called and told them that I was going to be traveling, and I still had a transaction decline, which isn't that fun. But we may need to actually pull in some of that data, and so for this, again, we'll get into the technology components in a moment, but we basically do enrichment in stream. So as the transaction's coming in, we enrich that particular record with whatever other information we need. That could be our past 20 or 30 different transactions. It could be our past 20 or 30 different transaction locations, right? I mean, a very simple fraud check is it actually possible for someone to have traveled the distance between the last two transactions? And then we can also do, in the online system, in this event processing box, based on the results of applying our model, we'll do alerting directly in stream from the online system as well that sort of supplements whatever we do in our offline or repository bit. And that all gets pushed out into our case management system. So event detection, it's part of the talk, so let's get into it a little bit. I mean, when I hear event detection, you think of machine learning and statistics, all this sort of stuff. This is not really a data science talk, and I won't get into all of the details of it, but it's important just to kind of understand it, I think, a little bit. Quite simply, it's, we're trying to detect if some sort of event of interest has occurred, and usually, well, it's typically temporal or spatial or both. So as I mentioned before, it's either some kind of a distance type thing or some sort of time-based event detection. The problem in the fraud space is that there's a very high number of non-events. Most of the transactions that go through are actually not fraudulent, right? And so if we had really good labels and we knew exactly what a fraud event looked like every time, we could do a pretty standard supervised machine learning. But this sort of high number of non-events puts us into this category where we're in this semi-supervised machine learning. And I think the reason why I'm bringing this stuff up is that the key point in this type of system is that you obviously want to optimize for accuracy, but you really have to be careful about false positives. And I can give you a concrete example of this. There's a fairly new investment bank, but they're also rolling out debit card services in the US, and they have some very, very, maybe their debit card account is pretty minor, but their investment accounts are very large, right? And so it actually can be more expensive to decline the transaction. A customer gets frustrated and said, you declined my thing, I'm moving all my money out, right? People are somewhat irrational. So it actually can be more expensive to deny a transaction, even if it's potentially fraudulent, right? And so you kind of have to monitor the model very closely to make sure that you're not getting too many false positives, which means you need to be able to do pretty frequent updates to your model. Making sense so far? So, generally speaking, right, we learn the model for some expected signal value, calculate a score based on that event, and either alert or don't on the event. But generally speaking, we'll send back the score to the source system, and then it has rules for exactly what constitutes a decline transaction. But most of the time, what we're doing is flagging potentially fraudulent events. Pretty simple, right? Yeah. So some numbers on the particular system that I worked on that we do this. Sorry, I can't disclose who that is, but we do all of the event processing has to complete in less than 500 milliseconds, and this is actually pretty generous. The one thing that we let be more than 250 is the check sort of deposits, because it has to do some image processing. That takes a little bit longer, and we actually outsource it, so it goes over a REST call, outside the data center, so that takes a little bit longer. We do actually that's the wrong word, it's about 400 million events per day. Each one of them is separated into different flows depending upon the stream. Right now we're at about 2,000 sustained transactions per second, although that obviously varies with how shoppers buy things, right? But projected over the next 6 to 8 months, we should be up to around 10,000 transactions per second, which isn't really actually a ton, but it's enough. Each flow has at least 3 steps. I kind of talked about these. There's an adapter step. There's a persistent step out to our reference data that I mentioned, and there's a Hadoop persistence. And then the one that I mentioned with the check deposits is the most complex with about 7 distinct steps. So now into the fun part. Okay, so the first generation that we built on this is really kind of getting into the technology stack a little bit more. We used to use pretty simple Java, Spring integration to convert from whatever the source system is into our message format. And then each one of the event detection flows is really just run in a JVM. Just basically, pretty standard TC servers on blades that does all of our event detection code. Now, the rage right now is, Spark streaming and Storm and, SAMZA and all the stream processing stuff. And we'll probably get there at some point. But you just can't beat the simplicity of, basically having all of your state in a single JVM for doing event processing, right? You start implementing distributed systems on top of this, and you introduce a lot more potential points for failure, maybe. So for right now, this is kind of how we have it set up, and it's pretty simple. We use HBase as our reference data store, and so basically we're doing a get on the customer ID and getting their last transaction history and whatever sort of ancillary other information that we want. And in the first generation, we were actually doing the puts back to HBase and stream. So one of the things is like, if we check their balance, right? There's no point in doing much fraud detection if they don't have any money in the account. So you have to kind of do that. So the models are basically generated via SAS, served up as a REST endpoint, but ultimately in memory. We use a Flume Avro RPC client, load balancing RPC client. Just some other pieces of the stack. Again, I mentioned the supplemental stuff just comes in either via files and scoop. And then we have web applications that are built on search. So we pull things in and index things via the Flume Morphline Solar Indexer to do faceted searching for forensics. And then we use actually Impala via JDBC as well. So if you kind of look at it too, our Flume configuration gets a little bit tricky because when you start designing these things for multi-data center, each one of these JVMs, and so like an individual machine may have like 10 or 12 different JVMs. They don't actually take up very much CPU to do the event processing, and we tend to get these like pretty beefy servers to do it on. But each one of them is basically pointed to n number of other agents, and the way we have it set up, there's the edge node of the DR cluster is actually we're writing to the production HDFS cluster via those Flume agents just for a little bit of fault tolerance across data centers. And then, of course, we also have the ability then in the background to do DistCP across the different data centers, right? So once everything goes into the primary cluster, it's then copied over to DR. So that was our kind of first pass of this, and actually it works pretty well. But just the challenges along the way is that fraud prevention, right? Not detection, but prevention is pretty tough because of these response time requirements. This is my really badly not to scale diagram, but anything in this sort of sub 500 milliseconds is what I would consider prevention, and it's pretty hard to do there. Again, there's a pretty big risk of false positives. And it gets lower, I wouldn't say low over here, but it does get lower the farther out you go. So you need to make sure that any of the components that are in this type of system are capable of handling events at very, very low latency. Additionally, we've seen disruptions in downstream systems that sort of impact our processing, which makes people angry when they're sitting at the terminal waiting for the transaction to come back. Problems do happen with HDFS. We were initially on a multi-tenant cluster, and sometimes people do crazy things. They load tons and tons of small files and blow out file descriptors, and then Flume has problems writing to agents. Channels get backed up, that kind of stuff. Our initial pass did a SAN-based file channel for Flume. Problems with the SAN caused some issues with the upstream system. It's again this problem that we mentioned at the beginning, where we have these sort of somewhat tightly coupled applications. Additionally, because we're doing alerts out to case management, we're sending alerts out to alert management. It sort of we're taking in different sort of formats from our source systems. Whenever we have multiple systems, it does increase complexity because we kind of have to keep up with each one of those endpoints, if you will, in a different sort of a way. So whenever you're obviously integrating a lot of different systems together, it does become a little bit more challenging the more sort of touch points that you have and the more different ways that each one of these systems want to communicate with one another. The other thing is this has all of the transaction data for the bank, pretty much. Right? So other systems absolutely can use this data. It can be used for customer events. It can be used for the the beautiful customer 360 that everybody likes to talk about, right? You have all of their transaction data right there. And every time that another application comes on board and wants this, we have to like either provision them in Hadoop or set up their own kind of feed or something like that. It just causes sort of extra challenges. And our Flume-based ingestion implementation, it works, but it kind of just works for getting into our Hadoop cluster, right? If there's anything else that needs this data in the bank, and you can probably imagine some scenarios where that would be, we're kind of out of luck. The second is kind of related, I guess, to the third, but it's just that, having all these different types of system along the way, if we kind of first go from source systems to Java to, we also talk to HBase, and then we go to Flume, and then we go to Hadoop, and then maybe we send something off to case management. Tracking metrics about exactly like instrumentation across the system is actually quite challenging. And as all of you know, if you're developers, it's always good to instrument your code. You should instrument your systems as well, so you can try and determine exactly where those bottlenecks come in. Additionally, it's not just the instrumentation, but we actually need to make sure that our raw numbers are trued up. So everything that we're putting into our reference data store, like we're putting into HBase, we need to make sure that we're not losing messages, that there's no problems along the way, and so we have to do some kind of reconciliation along the way. And that was kind of one of the issues. Setting up Flume monitoring, that kind of stuff was a little bit of a challenge. So this is kind of our second generation. Still a little bit in process, but this is the proposed architecture. Sorry about the fonts there, Kafka. So basically we have our incoming events, and they go to, let's see if I can get this to work. Kafka, so our transactions go to a Kafka cluster. So we've kind of basically made that initial layer of that integration layer just to be Kafka producers. So they sit out on the source systems, or we provide an API for them to write directly to it. And then we push those messages to Kafka, goes into our event processing. We do our reference data hookup from HBase. Notice that we're actually only just now doing the gets from HBase. We call out to our machine learning models, right? So it's kind of in memory, but we expose it via REST API. And then it's back out, right? And that's the basic flow now with Kafka, right? So we bring stuff in, do the event processing, grab do the enrichment, update it against the model, and then we push out the result back out to Kafka. So that's the simplest kind of way. But this allows us a lot of sort of efficiencies in that now we can just pull the raw transactions directly from Kafka, so it's not actually tied into the event stream. We're not actually waiting for to make sure that Flume has sent that message on along. We just write it the one time to Kafka, and then it gets pushed out to HDFS. Additionally, we've now asynced our updates to HBase, so we don't have to do the puts directly in stream. And this is important because if any of you have ever worked with HBase or like any NoSQL data store, batching drastically improves throughput. So this has given us a lot less pressure on HBase. If you're trying to do single row puts on HBase, I should have had a graph on this, but they're really bad, right? Benchmarking single row puts on HBase are pretty bad. Whenever you can batch them up, you can do it a lot more efficiently. So this gives us a lot more kind of operating room. The biggest thing in this type of system, I'm sort of digressing a little, but as it relates to HBase is like long tail SLAs. So you need to make sure that your 99th percentile is still low, right? Because any disruptions, if suddenly a get that was taking 20 or 10 milliseconds is now taking 1 or 2 seconds, it's a huge difference, and it can kind of muck up your event processing. And we can also now, as we move towards using kind of Spark and MLib and those kind of things to do other models, we can actually use Spark streaming and have our Spark streaming kind of infrastructure pull the updates the transactions directly from Kafka as well, and update the model in real time. So like right now we just sort of do batch offline model building, but as we sort of advance the technology and roll things out, I mean as a bank after all it takes a while. So we'll get to that state where we'll be able to then be doing sort of real time, or I hate real time, near real time updates, whatever, in stream. Additionally, our application can write our alerts directly back out to Kafka as well. And so if we have any alerts that we're generating from our offline system or updates to case management, we see a pattern analyst says send this, right? We can do that. Of course, we can basically run that alerting and case management directly from Kafka as well, so we can send out things like automated text messages. We see a transaction come in. It wasn't quite high enough on our scoring algorithm to completely decline it, but it's a little bit suspect. You'll get multi-channel notification if you have that configured at your bank. So you'll usually get an email, a text message, and maybe a phone call. So we can now run all of those from Kafka as well. So this sort of architecture has, simplified what we were doing before because it kind of standardizes or standardize on Kafka as our message bus. And it means that everything really just has to be a Kafka producer or Kafka consumer, and we have an easier way to deliver things, or at least a standardized way. Maybe we won't say easier way. At least a standardized way to deliver things across applications. Oh, there's other. Don't forget number 9. So I'm going to kind of skip this diagram because I don't love it. So when we are building out this kind of system, these are sort of this is my like version of Kafka tips, I guess. Sort of considerations for building this type of system. I think it's really important, and the reason I put it this first is the data exchange. And what I mean there is that whenever you have these multiple systems talking with one another, you can benefit from some type of common exchange format. And choosing this standard, I think, has really drastic implications. There are a lot of places I know that start out with JSON. In my opinion, this is what I think should be the goals of your data exchange format. You should be simple, flexible, efficient, change tolerant, and interoperable. There's this really great quote from Dimitri at Twitter. He says, I'll just read it. Schemas are an impediment to moving fast the same way streetlights are. I think he means traffic lights. Useless if you're alone, critical when there's 100. I can't agree more. Don't use JSON for your message formats. There's a number of different reasons. Use something like Avro. It's a data serialization system. Everyone here knows Avro, right? Raise your hand if you've never heard of Avro before. Okay, there's literally one person in the whole room. So use Avro if you don't know much about it. It is a little bit more upfront than there's a little bit more upfront developer time than using JSON, I suppose. But I have this here in asterisk. Data is always accompanied by a schema. That doesn't mean that when you're sending a message in Kafka that you insert the actual whole Avro schema with it. Do this. Build a schema registry whereby you have essentially the ID of the schema embedded in your message. There's some open source versions out there. Confluent has one they just released. There's kind of a somewhat dead project out on GitHub. It's more like a schema repo. Basically, this is the gist. Store your Avro schema somewhere, expose a REST interface that kind of matches what everyone else is doing. You can store it in anything you want. They're pretty simple to make, right? I mean, you're just basically taking in these schemas, putting them somewhere, and then having some way to look them up. So you can do it in HBase, you can do it in Oracle, you can do it in Kafka, you can do it in HDFS, however you want to do it. Expose that REST interface, and then the cool thing I actually like about using your own, or forking one of the other schema registries that's out there is that you can input whatever validation rules you want on how developers are writing schemas. So if you want to make sure that everyone always has XYZ fields, then when someone tries to write a schema, you can parse the schema and do whatever custom validation that you want in there. They're pretty straightforward to build. I mean, if you have a couple Java developers, they can knock one out in a couple days or less. Second key point is it's very important. One of the reasons why this system I think is attractive is because we can provide common libraries for Kafka. There's all these different Kafka clients out there. There's Python, Java, Scala client, etc. Standardize, find a group that's interested in doing this and standardize and develop a producer and consumer library that you can sort of give out to people. So the people aren't individually, your developers aren't individually worrying about exactly how to deal with Kafka, right? And so this producer consumer library would do things like, understand about your schema repository, have methods to register schemas for you, have methods to consume those schemas, do things like insert timings at every step along the way, which we'll talk to in a moment. So take a little bit of extra time, develop these common libraries, and that way you're sort of saying, okay, anyone that wants to get at this data, this is the library that you use, follow this, and we've sort of simplified our deployment model for all of our different applications. Okay, this is kind of important. If all of you have heard of Kafka, hopefully you know this, but understand durability guarantees and delivery semantics. And basically, Kafka supports 3 levels of durability, and it's sort of defined by this parameter request required acts. The highest is that we haven't talked about what an ISR is, but we mentioned earlier that the Kafka is replicated, and the unit of replication in Kafka is a partition. And so when a producer is writing a message and doing a write, If the acts for that particular topic are set to -1, what we're going to do is make sure that every single replica for that partition has received the write, right? No one ever does no acts required, at least not in this kind of system. But I guess there is a scenario where you may do the medium, right? Like if you think back to the diagram, the source system, we may do our act set to 1, which is where basically only the leader acknowledges that it got a message. And the reason we may do that is because that source system is essentially waiting to get a response back for a particular transaction ID. And so we may just send it, and knowing that we have to respond back in 500 milliseconds, and we don't really care about waiting for the other 3 replicas to get that transaction. All we care about is the final replica, the final transaction after it's been enriched and after we have the actual score, right? So there's some trade-offs that you could do. A sane configuration down here is set your replication to 3 or so, be able to tolerate some failed, at least one failed broker, and have it such that all the replicas in the in-sync replica list have to respond back when a message is produced. Just to give you an idea, put this in context, this is on a really not that great of a cluster internally at Cloudera. So this is the sort of 3 times synchronous replication. We had an average latency of, they're sort of wonked off, but 379 milliseconds. We can absolutely tune this with adding more partitions, more brokers, that kind of thing. But still tons of records a second, 500,000, which is way more than we need for the system that I mentioned. I said I'd talk about delivery semantics, so here we go. The default in Kafka is at least once, so it's kind of what we're related to what we were just talking about. Messages are never lost, but they might be redelivered. Exactly once is really hard to do, and it comes with a significant sort of cost, I guess, if you will. Some people say it's impossible without a 2-phase commit and the producer sort of being aware of the consumer downstream. But there's sort of some things you can do to counteract it. So when you're thinking about delivery semantics, you have to think about it. The guarantees when you're publishing a message, but also when you're consuming a message. Like, so for example, the easiest case to think about is what happens if your producer sends a message, Kafka gets it, right, and has written it, but before it's able to send back the act, for whatever reason, you have some sort of network blip, or for whatever reason, the producer doesn't get back the act that it has actually written, in which case, you're going to want, because Kafka provides at least once, your producer's going to retry the connection, so you would end up with a duplicate message. So there's some strategies here. You could use a single writer per partition, and then whenever if you had a network hour, you could check the latest offset. Again, it's a little bit expensive to do that. On the consumer side, probably the easiest way is if you have some type of UUID, you'll deduplicate on the consumer side. This is easier with HBase, right? Because if you essentially use your unique transaction ID inside your row key, you can just do an update, right? And HBase will just version it, so a little bit easier to handle when you're writing directly to HBase. Okay, there we go. My third tip is build in auditing from the start. We can use Kafka in stream, as I mentioned before, as you're building out this producer and consumer library to save some batch operations later. And again, all these will sort of increase the initial development time, but I think will pay off in the long run. So for example, put something like this in all of your schemas, right? And this is what I was talking about before with the validations. So you can enforce that, we have a timings field that's just a map in Avro, and then every time another hop comes through, we just grab that record and update a value in the map. And this gives us like basically easy bake in stream analytics about sort of how long each section of our pipeline is taking, right? So this is sort of, we instrument as part of our message processing flow. The next step bullet is to adopt the LinkedIn style auditing. I won't really go through all of that, but they have a pretty good, some good blogs out there on how they've done it, where it's basically like every producer sends a message and they have a separate audit topic, and then there's a separate audit consumer, which reads through those messages and does some reconciliation on the counts and then reports out to their dashboards, right? So it's pretty easy to do. Again, as you're building your custom producer library, you could optionally write out an extra record to an audit topic, and you could have a standalone audit consumer that's essentially consuming from all topics all the time and truing up the counts that you should be getting for each topic. So I would encourage you to check that out. Okay, this is it's sort of near and dear. We still use Flume, actually, for the ingest to HDFS. It's pretty easy to get started. Flafka is the name of Flume that we came up over beers one night, but obviously Flume and Kafka. And so what we did in sort of the Flume 1.5 or 6 or something, we basically made it such that traditionally there was a memory channel and there was a file channel, and now there's a Kafka channel. And we also have a Kafka source and a Kafka sink. So if you're not familiar with Flume, you can basically do declarative configuration, so zero coding hookups to Kafka. The architecture of Flume is such that there's these sort of 5 components. There's sources. There's a thing called an interceptor, which is actually pretty cool. Interceptors let you do per event processing as the event comes in, so it's a pretty simple interface, just as intercept event, and you can plug in whatever custom code that you want to do there. So you can plug in things like indexing to Solr, and so it's a little bit confusing because you can use Kafka in a number of different places. You can either set up a Flume agent such that it's pulling messages from Kafka and then using the HDFS sync. So there's a blog out there that goes through all this and has the configuration and everything. If you search for Flafka, I'm sure you'll find it. But you can also just go direct to HDFS. I think I have that slide. No, I don't. Wait, how do I go back? Can I go back? Yeah. So what you can also do is just sort of cut this piece all the way out. If you don't really care about doing interceptors and selectors and message routing, you can just set up Kafka as the channel and write directly into HDFS. So that's pretty cool. But if you wanted to say read something from Kafka, do some sort of little bit of processing, maybe add something to the header, and then write it back to Kafka using the Kafka channel, you could do that too. So it's pretty flexible. It kind of saves you from some overhead from writing basically custom code. Big thing, benchmark based on your message size. This is, again, just some testing that we've done, but this gives a good idea. You can see that the number of messages per second really starts to go down pretty drastically the larger your messages are. I think this is a little bit more telling. This is the throughput in megabytes per second. If you can't read this, this is megabytes per second, and this is the size in bytes. So you see once a message is about at 10K, you sort of start to drop off. So make sure that what you're sending is relevant, and you can kind of draw your own conclusions from these charts. The next to last one is take the time to set up Kafka metrics. Kafka internally uses Yammer metrics, although there might be some things that change about that coming up here pretty soon. But it emits a ton of metrics, so use something like Graphite or whatever your favorite sort of JMX metrics tool is. You can measure things like the consumer lag, message in rate, bytes in rate, bytes out rate, that sort of stuff. You can publish your own as well. The new consumer producers have their own metrics, so it's a little bit of a hassle in my experience because I don't have like much of a background in setting up things like that, but it was well worth the effort to do it. So I would recommend that you kind of explore that, not to like plug Cloud Era Manager, but next version we do have some built-in metrics for Kafka as well, and we'll be adding more as time goes on. The last bit is security. So to be totally honest with you, that's pretty weak. It's pretty generous. There kind of really is no security built into the open source project right now. So currently we're sort of relying on network security, but it's a real hassle. We have upcoming improvements that are adding Kerberos support, authorization at the topic level, in addition to SSL as well. So if those are something that you are dying to have, just wait till next release, hopefully, cross your fingers. If you have opinions on this, it's literally under discussion today on the discussion list. So feel free to chime in. So again, just to recap, we talked about some of these challenges. I think that implementing a system like Kafka that's very low latency helps us with our prevention and allows us to keep continuing on our event flow with very low latency. We've sort of decoupled writing back to HDFS. We've decoupled problems in downstream systems because all we're really concerned about is getting the message written into Kafka. Again, because we've standardized on a producer library, standardized in one way to go and get at things. It sort of simplifies this a little bit. It's very easy for other consumers to spin up and grab the data, relatively. And if you do what I suggest and build in some of these metrics and auditing ahead of time, it makes it a lot easier to track how your messages flow across the system. I have 50 seconds to spare, and that's it. Thank you guys very much. Appreciate it. So if there's any questions, I'm happy to take them now, or if you guys are trying to get out of here, I'll stick around up front. But anyone have any questions, generally speaking? Yeah, there's a gentleman over here who has one. Excuse me, can you help him with the mic, please? Oh, he has to help up there. You can just yell it. I'll repeat it. I'll repeat it, sure.
I noticed in the first generation you have used the string integration in JSON like then yeah, you skipped it I guess in the second generation. And I was wondering, have you investigated spring text which practically brings string integration but also provides a nice integration with Kafka with Avro and stuff. You have all components and you might have been able to glue the stuff easier if you have used it.
Yeah, exactly. So the question.
Third generation.
Yeah, exactly, right. So the question was, I talked a little bit about Spring integration earlier. Had we looked at the Spring XD, right, to do that, because it has some built-in Kafka integration, right? The answer is yes. I think we'll probably be implementing that at some point, but not quite yet. Fair enough? Any other questions? Yeah. You can just yell, I can hear you.
You showed this graph how the throughput of Kafka was affected by message size. Does that also affect the latency in some sense, where the logging and so on gets heavy pressure?
Yeah. Well, so it can affect if you have your ACK set to -1, right? It can affect the latency from when you get an ACK back from the producer. So you'd have to kind of like basically tune your replica fetcher threads. But yeah, it absolutely can. I mean, think about it, if you have just tons of really large messages, right, and you can't keep up copying across the network, I mean, it's absolutely possible to saturate a 1 gig NIC with Kafka, right? I mean, it can happen. So yeah, so that's why I said benchmark, right? You'll have to figure out what's going to work for you and what your latency requirements are, right? So I mean, I've personally found that the smaller we can keep the messages, the better off we are latency-wise, and we can tune it down to the sub, 10, 15 milliseconds from when we produce a message, right? All right, sort of our HBase timings are 10, 20 milliseconds, usually 20, 30, and then we can do Kafka 10, 15, something like that. Any other questions? Sure.
How well does Kafka cope with one topic that takes up nearly everything of the volume traffic?
How well does it?
Like in a scalable way.
Yeah, so the question was, how well does Kafka handle if one topic takes up all of the traffic? Is that right? Relative to what? The impact on the other topics? Is that what you're asking? So if you had one topic, right, that was taking up all of the traffic, you would probably likely scale the number of partitions to match the distinct number of consumers, right? So that's kind of usually how we basically scale out the number of partitions to match up for those consumers. So I'm assuming if you knew that all that was going to happen, you would just build it that way, and so it should be fine. I'm not sure if I understand 100% your question. So can we talk after? Is that all right? Yep.
What tool do you use to monitor Kafka services?
The question was, what tool, I'll get to you in just a second, what tool do we use to monitor Kafka services? So right now, CDH includes Kafka support, so you can deploy it as well. And in CM5.4, we do some metrics as well. They actually use Graphite to monitor some, right? So that's what you're asking, at least the metrics. So like a Graphite collection reporter, but you could use like Ganglia or whatever your sort of tool of choice is, right? What was your question?
Did you use any other frameworks like Kite or anything else for this project?
So, I mean, to the extent that we use the Solar Morphline indexer, I guess that's part of Kite, right? So we use that. I work with the ingest team a lot, so I really like Kite. So hopefully we will at some point. I think morphlines are pretty cool in general, and I think as we move into doing more stuff in Spark Streaming, we'll try and utilize morphlines to do ingest and stuff like that. But yeah, it's sort of the extent of it now. I mean, I think that what you'll see out of Kite soon, I can't guess this is on the record, but probably see better integration with things like the schema, I guess some kind of standardized schema registry and those kind of things. There's definitely, as you start building out this kind of system, right, you have these schemas that Kafka is using for Avro. It would sure be nice, right, if our Hive Metastore could use the same schema repo and Kite could use the schema repo, so that we can sort of make use of all these shared schemas.
So what was that open source project you said for registering schema?
Well, Confluent has one. So if you go to confluent.io, those are the folks who founded Confluent. Yeah, they're like folks from LinkedIn who broke off into their own thing, and they've open sourced one on their Confluent platform a few weeks ago. It's pretty good.
As a producer, how you can efficiently distribute the writes into the partitions? Is it like just to refresh the metastore, the metastore of the topics, or is there a better way?
So the question is, as a producer, how do you efficiently distribute the writes? So there's basically two different ways that Kafka does writes into the different partitions that you have set up. The default partitioner is round robin, basically, and in the past it was kind of round robin with a little bit of a stickiness, so it would pick a random one and then it would stick to that for a while. But the other way that you can do is by a sort of it's called semantic partitioning. The default way to do is you would provide a key. So in the API, you can actually provide a partitioning key, and the default is just a hash on that key. And so assuming you have some kind of reasonable distribution, that gives you some other benefits too. Like if because the way that Kafka does writes, that they're only the ordering is only guaranteed within a particular partition. If you wanted to make sure, for example, that you always had every customer's stuff in order, you would partition based on the customer number, and then all those would be guaranteed to go to that same permission. So a lot of people, if you don't want to do the round robin partitioning and you feel like you have a pretty even distribution of keys, you can basically partition on that key, and then that'll split up the writes for you.
Okay, but yeah, can we just decrease the topic metastore refresh interval just to fix this issue?
The topic refresh metastore, I'm not following.
Because there is a configuration, you can just decrease the millisecond to every 10 seconds, you can just refresh this writes, and then everything will be written into different partitions. But the problem is that you should just refresh it every 10 seconds if you want to evenly distribute the writes.
Okay. Yeah, we'll have to. I'm not following with the metastore.
There is a configuration like topic metastore refresh interval, something like this too.
Okay. Yeah, I'm not familiar with that one, sorry.
Oh, yeah.
Anything else? It's right up here. Okay, hey, there's one in the way back. If everyone wants to leave too, you can go for it. It won't offend me. Yep.
It might be a really crazy idea, but Kafka has an infinite data storage, like never drop messages, pitfalls or stuff like that.
Yeah, I mean, you can do it, right? It just depends on how much disk space that you want to do. There's actually there's a configuration setting. It's the log retention. You can do it by bytes or by hours. Right now, it's like an integer, so it's some 247,000 years or whatever like that. So you can do it technically. We've had actually people on the mailing list talk about it. I guess it's not totally unreasonable depending upon how much data you're trying to store, right? Ultimately, you're kind of limited by your machine configuration. I typically recommend people do sort of Hadoop data nodes with 12 to 14 or so disks. So if you feel like across your cluster you can store things in more or less than that or whatever, or you want to scale out and do that, that's fine. Yeah, I mean, people have talked about it. I haven't ever seen it, but I mean, there's nothing that's stopping it, although there are some hard limits on the number of partitions. Well, not hard limits. There's some things that I've heard from the guys at LinkedIn mostly about like max number of partitions that you'd want to have, and it tends to sort of start falling over. I think the number I heard was around like 10,000 partitions, if that's right. I may be wrong on that. But there's some stuff out there that you can read about it. So if you feel like you're going to always stay under there and want to use it like that, right? I mean, like one way you can do a schema registry is to, if it's a pretty small amount of data, is just read it into Kafka, and then on spin up you just read it into memory. So I don't know how much data you're talking about, but yeah, I mean, I guess it's reasonable. Okay, anything else?
One question about Solar. How performant is Solar while indexing? I mean, if you have so many files on HDFS,
Yeah.
I guess you're using MapReduce to index, right?
No, so we do actually. So the question was how performant is Solar? Generally speaking, Solar and HDFS so we try and cache stuff in memory, right? And the way that we do the writes is we essentially are doing the write in real time, and then we switch them, right? So we just flip back and forth. Does that make sense? So we can have like 2 copies of it, and we are writing in real time. We use the Flume Solar indexer, and then we switch back over when the writes are done for that particular index. Make sense? Yep. Anybody else? Cool. Hey, thanks everyone for coming. It was a blast. Appreciate it. Thank you.